Okay, in this lesson we're going to talk about the nature of light. So light can act both as a wave and as a particle. When it acts like a wave, there's a couple terms that we need to understand as far as parts of a wave. We went over this in class, but a quick review. So here's my wave. Here's my equilibrium point, sort of the midpoint of my wave. The point at the top, here's the crest. The point here is the trough. The point from one crest to another crest is the wavelength, denoted by lambda. We can also have wavelength trough to trough. The distance between the crest and the equilibrium, or the trough and the equilibrium, is our amplitude. This is also our amplitude. And a cycle is from the midpoint to the midpoint again, but it includes both a crest and a trough. This is one cycle. So now let's compare two waves. So if I have this wave, I have my equilibrium point, and I have this wave. Wave A and wave B. Wave A, if I look at its wavelength from crest to crest, and if I look at B's wavelength from crest to crest, A has a longer wavelength, whereas B has a shorter wavelength. This means that A is going to have a lower frequency, which is denoted by nu. B is going to have a higher frequency, because what frequency is simply the number of cycles that a wave completes in a given amount of time. So if I were to look at these two waves, in these two time frames, A is going to complete 1.5 cycles, well, 2 cycles, while B is going to complete 1, 2, 3, 4, 5, 6, 7.5. So B is going to complete more cycles in the same amount of time than A. So B has a higher frequency than does A. So frequency and wavelength have an inverse relationship. As wavelength increases, frequency decreases. As wavelength decreases, frequency is going to increase, which is an inverse relationship. So frequency depends on wavelength. No matter what else changes about the wave, if the wavelength remains constant, the frequency will remain constant. But if the wavelength changes, then the frequency is going to change. So if we were to look at the relationship between the wavelength and the frequency mathematically, we would do so using this equation. C equals lambda times nu. C is going to be equal to our speed of light, which is a constant. So the speed of light is equal to 2.998 times 10 to the 8th meters per second. Our lambda is going to be equal to our wavelength, and that is going to be typically in meters, or it could also be in nanometers. But because C is in meters per second, most often we're going to want to convert our wavelength to meters. So if it's given in nanometers first, you're going to need to convert to meters. And then we have nu, which is our frequency, and its units are hertz, or 1/second. So what hertz means is our frequency in hertz is how many cycles a wave can complete in 1 second. So before we talked about frequency being the number of cycles that a wave can complete in a given amount of time. Well, now that given amount of time is constant. It's 1 second. So which is why our hertz can also be denoted as 1/second, because a hertz is how many cycles a wave can complete in 1 second. So we may have more than one cycle, we may have less than one cycle. So let's do some practice with using this equation. Okay, so let's look at this example. What is the wavelength of radiation with a frequency of 1.5 times 10 to the 13th hertz? So we're going to use our C equals lambda nu equation, and we're just going to plug in the numbers that we have with our units. So we're going to have C is 2.998 times 10 to the 8th meters per second equals our wavelength. We don't know, that's what we're solving for. So lambda times our frequency, 1.5 times 10 to the 13th. And to keep my units consistent, since I have seconds over here, I'm going to write, instead of hertz, I'm going to write 1/second. Okay, or I could also write it just as per second. So now I'm going to divide 1.5 times 10 to the 13th over S divided by 1.5 times 10 to the 13th over S. So my seconds are going to cancel, so I'm going to be left in meters, and when I do this calculation, I'm going to get 2.00 times 10 to the negative 5th meters equals my wavelength. Okay, now I want you to pause the video and I want you to do these two practice problems on your own. You can work together with your partners, but go through them. Use your C equals lambda times nu to figure out the answers to each of these practice problems, and then when you think you have them figured out, go ahead and restart the video, and I'll go through how to solve these. Good luck! Okay, so pretty quickly, because hopefully you were successful in solving both of these problems. So for the first one, what is the wavelength in nanometers of violet light with a frequency of 7.26 times 10 to the 14th? Sorry, that should have been 10 to the 14th hertz for frequency on that. So we've got our C equals lambda nu, so C is 2.998 times 10 to the 8th meters per second, and that equals lambda, which we're trying to find, our wavelength, times nu, which is our frequency that we know, 7.26 times 10 to the 14th hertz, but because, once again, I've got my seconds over here, I'm going to keep this over seconds. So I'm going to divide both sides, 7.26 times 10 to the 14th over seconds, divided by 7.26 times 10 to the 14th over seconds. And I will get a wavelength equal to 4.13 times 10 to the negative 7th, and my seconds canceled, meters. But this question asked for the wavelength in nanometers, so I have to do a quick unit conversion. So 4.13 times 10 to the negative 7th meters times, meters on the bottom, nanometers on the top. I know that 1 meter is equal to 10 to the 9th nanometers. So 4.13 times 10 to the negative 7th times 10 to the ninth, and I get 413 nanometers as my frequency, which is my final answer. For number 2, I have blue light with a wavelength of 400 nanometers. So once I get, again, I'm a nanometer, so I'm probably going to have to convert that, so I'll keep an eye on that. So I need to calculate its frequency. So again, C equals lambda times nu, 2.998 times 10 to the 8th meters per second equals, and I know the wavelength this time, 400 nanometers times nu. But I need to get 400 nanometers into meters before I can use it. So times, I've got nanometers on the bottom, meters on the top. 1 meter equals 10 to the 9th nanometers. So 400 divided by 10 to the 9th gives me 4 times 10 to the negative 7th meters. So I can plug this back in. 2998 times 10 to the 8th meters per second equals 4 times 10 to the negative 7th meters times nu. Divide both sides. 4 times 10 to the negative 7th meters. 4 times 10 to the negative 7th meters. My meters will cancel, and I will have, it's a little smaller, and I will have 2.998 times 10 to the 8th divided by 4 times 10 to the negative 7th, and I will get a frequency of 7.495 times 10 to the 14th 1 over S, or hertz. Same thing. If you just write hertz, that's fine. If you write 1 over S, that's fine too. But typically when we write frequency, our units are going to be in hertz. You may also see this written, you may also see this written as S to the negative 1. So 1 over S, hertz, or S to the negative 1 are all the same units, meaning hertz essentially for frequency. All right, so that's it. We've covered the mathematical equations for relating frequency and wavelength when light is acting like a wave. In the next video I want you to watch, we are going to look at what happens when light acts as a particle and how it behaves and what equations we need to use to express that mathematically. Okay, so flip over to the next exciting video in our installment and look at the nature of light.